In this video, we'll talk about vector spaces. Vector spaces have some requirements to be vector space. Basically, vector space is a set with elements called vectors. Although these elements, although they're referred to as vectors, don't necessarily fulfill the requirements to be seen as vectors in the traditional sense, like that's n tuple, some amount of entries inside like a usual style vector. It can be also, for example, normal numbers. Just the requirements for vector space have to be satisfied, something like axioms, and we'll outline them right here. So let's say we have a set V being a vector space, and there is U, V, and W. There are three vectors, and for any three vectors U, V, and W, any three different vectors U, V, and W in V, we have some requirements. Also, there is a field F. That field is very commonly, very often, for example, real numbers. And from this field will come some scalars. Let's say you will use scalars, different scalars A and B. They both belong to F. So for any U, V, and W in the vector space V that directly belong as vectors to the vector space V and scalars A, B in some field F, we have some requirements in order for V to be a vector space. First and foremost, U plus V will equal to V plus U, meaning there's commutativity under addition. Then there is also associativity, meaning this. The order of addition doesn't matter. And then there is some more requirements. There exists some 0 in V, such that 0 plus U will still be U. There also exists some minus U in V, for every U in V, such that minus U plus U will give this 0. Also, there exists multiplicative identity. So not just additive inverses, but multiplicative identity in V such that 1 times, in V for every U, by the way, not mentioned explicitly here anymore, but that's meant that way, such that 1 times U is still U. And then there's also closure. There's closure in the way that any addition of two vectors, of some vectors in V, well, that will still belong to V. So when we take U plus V, that still belongs to V. Also, there is scalar closure, scalar multiplication closure. That means that for some scalar A from F, AU will belong to V. Another thing about scalars is also there is associativity of scalar multiplication. So this is for scalar multiplication, by the way. If you multiply by scalars, that will still belong to V. But the closure that's closed in V. But perhaps multiplicating the vectors by each other does not necessarily guarantee that it will belong to V. So this is a requirement, a multiplication by scalar that has to be emphasized. Then there is associativity of scalar multiplication, meaning that this means the same as this, and of course also belongs to V as a whole. Where this U is a vector in the vector space, an element of the vector space, and A, B are scalars from the field F. Although that's a general notation for a field, we can, for example, take real numbers R. And this also, of course, brings the idea that if A times U is in V, then, and also U plus V and U and V in V are close in V, then some linear combination with using the scalars and the vectors from V will be in V as well still. So these are some of the requirements for a vector space. Now, in order to perhaps illustrate it even further, we can look at some example. So example could be, for example, R2, which basically means real valued vectors with two entries. Well, what this means is that we can check these requirements on these vectors. So if we take vectors that have x1, x2, where basically x1, x2 are in R, then we can play with this and prove that the previously mentioned requirements are satisfied. So let's take some two vectors, for example, x and y, from this set. This set contains all two entry vectors that have their entries anything that comes from R. Well, x plus y should belong to V, where the V in this case is R2, which is a concrete example. So, does this get satisfied? Well, via the properties of adding vectors, this can be shown to just be satisfied. x1 plus y1 just becomes just one entry, x2 plus y2. Addition of two real numbers will give a real number, and basically what we have is two new real numbers as two entries of a new vector. And because our vector space only requires that it is a two entry vector with real entries, well, that's satisfied. So addition is closed. Then by some scalar, well, let's say it's over the field R, for example. So F will be R, the chosen field of scalars. Well, AB will be in R, or AB R in R. Well, we can just show this to work as well. A times x1, x2 will be ax1, ax2. Well, what this does is basically multiplies by another real number each of the entries. Well, that still is, this is a real number, this is a real number, therefore this belongs to V as well, this belongs to V. Alright, so scalar multiplication, that's closed in V, addition is closed in V. And those other things are also satisfied. For example, we won't go over all the requirements, but for example also the vector 0, 0 with two real entries, 0 and 0, is the additive identity. And that does work out because 0, 0 is contained in this V, in this R squared, R2. Alright, so there's more requirements that could be checked to be satisfied by, but we won't go explicitly over them now. And then in general, there's a very common type of vector spaces. That's in general what we now talked about, Rn. What it means is basically not only there's x1, x2, but there's x1 through xn. So it's n entry vectors with real entries. So Rn, it means in general a vector, a set of vectors where the vectors have entries that are real numbers and they have n entries. Alright, there's more examples of vector spaces that we could go over, perhaps in the next video, but this is it for introduction to look at what a vector space can be seen as through the definition, and you can try for yourself some more examples of vector spaces by verifying the requirements and seeing whether if they belong or if they are a vector space example or not.